Well, hey there, mathletes. Here we are looking at inverse of a function. Inverse of functions are going to give us an opportunity to go backwards from functions. So typically we have inputs and outputs. So our input values are our x values, and our output are our values that we get out, typically our y values. Okay, and our outputs are we define as our range. Okay, those are our possible outcomes, and our domain is our possible inputs. Okay, so as we're talking about inverse functions, we're going to be talking about ways of us going backwards to our original set. Okay, so let's look at the first thing we're going to look at here is we're looking at solving for x here. Think of f of x equal to x plus 3. Okay, so if I want to solve for x here for this function, okay, what I'm going to do is I'm going to set y equal to 2x plus 3, okay? And I'm going to solve for x. So I always like to say, I'm trying to isolate that value. So I'm going to pull away the layers next to it. Well, first thing I'm going to do is subtract 3 from both sides. I get y minus 3 equals 2x. Divide by 2. Divide this entire side by 2. And so what I get out is x is equal to y minus 3 over 2. Okay, so now this is useful because now if I want to find the input, so that's typically my x, when the output is negative 7, my y. Okay, so now it's a lot easier to use this equation to find our x value if I know my y value. So I can plug in my y being negative 7 minus 3 over 2. I get negative 10 over 2 equals negative 5. Okay, and that would be my x value. Okay, so when we reverse this equation, f of x, is useful for finding our y values when we know our x value. Okay, and so our inverse kind of works the other way around. It is solved explicitly for x, and y is kind of the independent variable that we're plugging in here. Okay, and then we get our x answer out. Okay, so that's kind of our foundation of thinking about our inverses here. Okay, so as we're thinking about these inverse functions, okay, think about switching the order of the relationships. So typically we talk about x and y relationships. Okay, x is a domain, y is a range. So with inverses, okay, we're switching that order. So now it goes y to x. And what was before our range is now our domain, and what was our domain now becomes our range. Okay, so think of this example. I kind of threw it together here. We think about your relationship between the number of hours you work and dollars earned. So if you have a job, most of your jobs are going to be, your first time jobs are going to be hourly jobs. So the more hours you work, the more money you make. Okay, so that would be our f of x relationship. So if we work 3 hours, make $45. That's our x, our y. Work 6 hours, make $90. So that's our function. So the inverse function would be when you get your paycheck back and you see how much money you made, trying to think back how much did I work to earn that money. So it's the inverse. We're not thinking about taxes and all that stuff that's pulled out, but just the cash out that we get. Okay. So with the inverse function, we're saying we made $45. Okay. What? How would I be able to figure out how much I worked? How many hours I worked going there? That would be our inverse function. So it's the relationship between how much you earned, $90, and the hours you would have had to work for that. Okay. So as we're thinking about inverse, okay, big thing we need to know is that the graphs are inverses, are reflections over our y equals x graph. Okay, so if you think about this relationship, we have our x and y values. So these are ordered pairs. We could write this as 1, -1. We think about the graph, over 1, down 1, we're here. Okay, this is 2, 0, 3, 1, and 4, 1 is there. Okay, so if we think about a inverse, okay, these are interchanged. Okay, our x's become our y's, and our y become our x's. Okay, but we still are going to graph them now as these are our x's and these are our y's. So notice they switched. And so when we graph -1, 1, we're here. Now it's 0 up to 1, 3, and 4, 1. We have these points there. So we'll always notice that the graphs of inverses will reflect over this y equals x line. Okay, so we'll see examples of that coming up. Okay, so as we're finding inverses, we want to think about that first example we did. But what we're going to do is, the first thing we're going to do is we're going to interchange our x and y's. Okay, so I take my function and I think, all right, change this to x, change this to y. So it's going to be x equals y squared plus 3. Now I'm going to solve for y, so I need to get y by itself. Okay, so I want to make y the argument. So I got to pull away these other layers. So I got to subtract 3, get x minus 3 equals y squared. Then we're going to square root both sides. Well, anytime I square root, I need to remember a plus and minus. Square root of x minus 3 is equal to y. So now that I have solved it for y, what this is actually is the inverse function. If we define this as our f of x. Okay. So as we look at this graph, notice we have plus and minus. So we have two graphs. The plus graph would be this half. Okay, and we know that that negative in front here, okay, is a reflection across the x-axis. So that's where we get the second part of that function. And when we talked about graphing these, we talked about these graphs being sideways parabolas. Well, that's exactly what they are when we graph them together, because they reflect that parabola of our original function, y equals x squared plus 3. Okay, and we reflected it over that y equals x line. Okay, so as our next example, okay, we're going to find these inverse functions. Okay, this f inverse, okay, is used. We don't necessarily call it a function because it might not be a function as we go around. Remember, functions need to pass our vertical line test. So if I go back here and we look at this, we know that this graph right here isn't necessarily a function, because as I look here, it doesn't pass my vertical line test, so it crosses twice, so it's not a function. Well, yeah, that's because we have two functions really happening here, a plus and a minus graph. So that inverse is not always a function. So here, with f of x being the square root of x plus 1, let's go ahead and find f inverse. Okay, so we're going to replace f of x with y. This is y equals square root of x plus 1. Now interchange it, your x and y. And if there's more than one present in your equation, if you're talking about a polynomial, all of them get interchanged. Okay, all y's will become x's and all x's will become y's. And then we're going to solve for y. So that means I need to isolate that value right there. Okay, so I'm going to pull away the layers. So parentheses, exponents need to be dealt with first. So my inverse operation of a square root is squaring, so I square both sides. Sorry, and then we get x squared equals y plus 1. And now we are going to subtract 1 from both sides. And we get x squared minus 1 is equal to y. Now, notice, for our original function, the square root, okay, that's a graph of something that looks something like that. It's half of a sideways parabola. Okay, that domain is x is greater than -1 because we had a +1 shift in our graph, a horizontal translation. Okay, and our range, okay, was all non-negative numbers because you take the square root of something. Actually, this was shifted over 1. Okay, we always get positive values, that the answers to these square roots are never negative. But now, when we look at these inverse functions, okay, what was our domain here now becomes our range of our inverse. So this is our inverse function. Okay, so the domain, okay, is this part, all non-negative numbers. So really, x is greater than or equal to 0. Okay, and our range is coming from our domain. So now we have to say y is greater than or equal to 1. Okay, because if you think now about our translation of our inverse, now we're talking about a parabola. That horizontal is now a vertical translation. This goes down 1. So when that parabola goes down 1 in our graph of our parabola, okay, our range, okay, has to be greater than, I missed my negative, right? There's a negative here. It has to be greater than -1. Okay, but our range, the inverse, doesn't actually include this part, because when you reflect over the graph in the green, it's only half of a parabola. So when you reflect it over, you actually only get this half because your x's have to be greater than 0. Okay. So finding inverses. So here's a couple of quick examples on finding inverses. So first thing, how I do it, I change it. So I know that this is going to be 2y and this becomes x's. So I interchange my x and y. I knew this was going to be y already, so I do that switch. Now I need to solve for y. So divide by 2, divide by 2. So I get y equals x over 2, which is f inverse of x. Okay, over here, so interchange them, so I get x is equal to 1/3 y minus 2. Now I get y by itself, so I got to pull away my layers, so I add 2 to both sides. And we get x plus 2 equals 1/3 of y. I'm going to multiply by 3 to both sides to undo the 1/3. And so I get 3x plus 6 is equal to y. Well, that is also equal to f inverse of x. Okay. So more about their graph. So if we find the inverse of f of x equals x squared, okay, x has to be greater than 0. Okay, and we do that because from the graph of the function and its inverse. So then we're going to do that. So here we have x equals y squared. So when you're trying to get y by itself, okay, we are going to square root both sides. And we get square root of x equals y, or our inverse. Okay. We don't have to worry about our plus and minus because we're saying that x has to be greater than 0. Okay, so when we do that, consider this graph. And using Desmos is useful if you don't have your graphing calculators at home. Notice our function here, f of x equals x squared. Okay. Well, if we only want x is greater than 0, that means this is actually not a part of our graph. Okay, so that's just kind of blacked out. So we only have that. So when we graph the square root of that, okay, we don't get this graph because we don't need to worry about the negative part. So that is why that one's dotted out. So you notice that our inverse, the square root of x, graph in the blue, is just that reflection over that y equals x line. Okay. So we have a horizontal line test. This is also known as a one-to-one test. Okay, and this is the test to see if our inverse is still going to be a function. Okay, so when we are looking at our parabola, so let's look at the case when the inverse is not a function. When we looked at our parabola, if we reflect that over our y equals x line, we would get the plus and minus answer, and this wasn't a function, and we don't like to work with things that aren't functions. It doesn't pass our vertical line test. When you plug in some x value, we could get one y answer or we could get another y answer, and we don't like to do that in math. We like to make sure we have functional relationships, we get the same answer every time. So to test if a function will have a inverse, okay, we do a horizontal line test. Okay, that means it should only intersect the graph one time, just like our vertical line test to test if a function is, or a graph is a function. So when we look at this other one, when it says it is a function, notice it passes my vertical line test, and it also passes that horizontal line test. Anywhere I draw a horizontal line, it only intersects that blue graph once. Because as I would reflect this graph over the y equals x line, we would have a graph that looks something like this, and that would pass my vertical line test as well, and so it'd be a function. Okay? But with our inverses, so again, we see our parabola does not pass our horizontal line test because it intersects twice, so its inverse is not a function. So that's why we got to restrict that domain and range. Okay, so consider the function f of x equals 2x cubed plus 1. Determine whether the inverse f is a function. So all I have to do is do my horizontal line test. Nowhere does it cross more than once. So it's yes, the inverse is a function. Yes. Inverse is a function. Okay. So that's our horizontal line test. Okay. Again, if we look at this, consider the function 2 square root of x minus 3, determinant, horizontal line test, it never does cross more than once, so it's also a function. Okay, our last example here is looking at, well, if somebody gives you a function, okay, f of x, and they say, well, is g of x the inverse of that function? Well, how do we determine that? So this theorem, okay, that's important to know with these is that if you take the inverse function and you make it as the argument, okay, you get the x out. It simplifies to be x. If you think about it like this, if a function, if you put it in and what you got in you put back, you should get back the value you got. Okay. So that should go either way. So if you do the composite function of f of g of x, it should be x, or g of f of x, and it should be x. Okay. So let's test these out. So the first one, we need to test out both of them. So f of g of x. So f, what is g of x? Well, g of x is this, x minus 5 equals, so my function f says whatever's in this space here, your argument, you put here. So we put an x minus 5. And then we have plus 5 here. Okay. Well, if we simplify that, the 5's cancel out, and that's equal to x. So we've checked that one off. Okay. The other way around is g of f of x. So what is f of x? Well, f of x is this. Okay. So g of x says take whatever's your x. So I have x plus 5. So it's right here, my input. Okay. And then I'm going to subtract 5 from it. Well, I simplify that out. That equals x. So therefore, I can say that g of x is the inverse of x. So that's how we can test if functions are inverses of each other. Go ahead and bring any questions to office hours. Take care.